Interference of light waves and Young's double slit experiment. Now let us discuss about interference produced by light waves. This experiment was first carried out by British physicist called Thomas Young in the year 1801. In Young's experiment, a monochromatic light from an illuminated slit S is allowed to fall on two symmetrically placed parallel slits S1 and S2 that are very close to each other and are at equal distance from the source S. The two slits start producing cylindrical wavefronts. Since the wavefronts produced by slits S1 and S2 are generated from a single original wavefront, the waves from slit S1 and S2 will have same wavelength, frequency and equal phase difference. Hence, they can be called as coherent sources. The wavefronts emerging from S1 and S2 will interfere in space and produce a pattern on the screen. The pattern will consist of bright and dark bands parallel to the slits. Such type of patterns are called interference pattern and bands are called the interference fringes. Now, if two waves of light arriving simultaneously at a point in space are in phase, constructive interference takes place. The intensity will be maximum at that point, hence we get a bright fringe. Similarly, if two waves of light arriving simultaneously at a point are in opposite phase or out of phase, destructive interference will take place. The intensity will be minimum or zero at that point, hence we get a dark fringe. In this way, alternate bright and dark fringes are formed on the screen. Now, in this experiment, if we close one of the slits, the interference pattern disappears and we see only a plain light on the screen. This shows that two coherent sources are required to produce interference pattern. Now, let us find the distance between two consecutive bright or two consecutive dark fringes. It is also called as fringe width. Here, let the distance between the two slits S1 and S2 be small d and the distance of the slits from the screen be capital D. The central bright fringe is formed at the point O. Since the point O is at equal distances from S1 and S2, the path difference at this point S2O minus S1O is equal to 0. Now consider any arbitrary point P on the screen. For a bright fringe at point P, the path difference between the two waves reaching the point P must be equal to integral multiples of the wavelengths, that is n lambda. Therefore, S2P minus S1P is equal to n lambda. Let's find S1P and S2P. From the triangle S2RP, S2P square is equal to S2R square plus RP square. We know that S2R is equal to D and RP is equal to X plus D by 2. Substituting these values in the equation, we get S2P square is equal to D square plus X plus D by 2 the whole square. Let's call this as equation number 1. Similarly, from the triangle S1QP, S1P square is equal to S1Q square plus PQ square. Here, PQ is equal to X minus D by 2 and S1Q is equal to capital D. Substituting these values, we get S1P square is equal to D square plus X minus D by 2 the whole square. Let's call this as equation number 2. Now, from equation 1 minus equation 2, we get S2P square minus S1P square is equal to D square plus X plus D by 2 the whole square minus D square plus x minus d by 2 the whole square. After simplifying this expression, we get s2p square minus s1p square is equal to 2xd. This expression can be written as s2p minus s1p into s2p plus s1p is equal to 2xd, or s2p minus s1p is equal to 2xd divided by s2p plus s1p. If the point P is very close to the center O and capital D is far greater than small d, then S1P will be almost equal to S2P, which is equal to capital D. Therefore, S2P plus S1P is equal to 2D. Replacing S2P minus S1P by n lambda and S2P plus S1P by 2D, we get n lambda is equal to 2xd divided by 2d. Therefore, x is equal to n lambda d divided by d. The distance of nth bright fringe from the center O of the screen is given by xn is equal to n lambda d by d. Similarly, the distance of n plus 1th bright fringe from the center of the screen is given by xn plus 1 is equal to n plus 1 into lambda d by d. The distance between any two consecutive bright fringes is called fringe width. It can be obtained by subtracting these two equations. Therefore, beta is equal to xn plus 1 minus xn, which is equal to n plus 1 into lambda d by d minus n lambda d by d. On simplification, we get fringe width beta is equal to lambda d divided by d. Similarly, if we calculate fringe width for dark fringes, we find that it is also equal to lambda d by d. Therefore, all bright fringes and dark fringes have equal width. If I1 and I2 are the intensities of individual sources from the slits S1 and S2, then the resultant intensity at any point on the screen is given by IR is equal to I1 plus I2 plus 2 into root of I1 I2 into cos phi, where phi is the phase difference between the two interfering waves. If I1 is equal to I2 is equal to I0, then the resultant intensity is given by IR is equal to 4I0 into cos square phi by 2. Now, for constructive interference, that is at a bright fringe, the phase difference phi between the two interfering waves is equal to 2n pi. Therefore, resultant intensity IR becomes equal to 4I0. Similarly, for destructive interference at a dark fringe, phase difference phi is given by 2n plus 1 into pi. Therefore, resultant intensity at a dark fringe becomes equal to 0. Note that all the expressions derived previously in the ball experiment are also valid for interference of light. The intensity variation curve in Young's double slit experiment is like this. Note that all bright fringes are of equal intensity given by 4I0 and all dark fringes intensity is found to be 0.